Hello, everybody. Good morning, all of you. So we'll start with today's quote. So it is by Sadhguru. Do not try to be the best. Just do your best. Anything when you do with some expectation, you will be always unhappy. Whatever be the type of expectation. So if you try to be the best, it may not be possible. And there is nothing like the best. And do your best, automatically you will do the best. And today is the birthday of Ernst Mach. I think all of you are familiar because of fluid mechanics and the CFD, whatever we are studying now, GTJP. So Mach number we come across often. So his birthday is today, and he's Austrian physicist and philosopher who established important principles of optics, mechanics, and wave dynamics. His early physical works were devoted to electric discharge and induction. Between 1860 and 62, he studied in depth the Doppler effect by optical and acoustic experiments. He introduced the Mach number for the ratio of speed of object to the speed of sound, and it is named after him. When supersonic planes travel today, their speed is measured in terms of that keep Mach's name alive. His lifetime interest, however, was in psychology and human perception. He supported the view that all knowledge is a conceptual organization of the data of sensory experiences or observation. And he says thought experiment is, in any case, a necessary precondition for physical experiment. Whenever you try to do the experiment, even your research or project or anything, when you have to do some physical experiments, first you have to have thought experiment. So in your mind, the experiment has to run, how it goes and all. You should have the visualization or imagination of what is going to happen before. So in brainless space, what is going to happen? P naught also is constant. Okay, and here what we assume is there is flow is free vortex or angular momentum is constant. So RCW is equal to constant. Okay, so these are the things we assume. So because knowing and CW at impeller exit, I can find out what is CW at diffuser inlet. So this gives me CW at diffuser inlet. So here what we do is we have to iterate assuming CR2, we iterate. Because knowing CR and CW will give you C, and so knowing C, I can calculate T. So I can calculate P using the isentropic relation, and then I can calculate rho, and then I can calculate CR. So A is 5 dB. So in that way, I have to get it and repeat the calculation.
Sir, not audible.
Sir, your video is lagging.
Lagging.
Yes, sir.
Mm, what to do? I cannot do anything. That is what I am writing. It is coming later. Or
Yes,
After
sir.
that arrow mark, you were stuck for 15 seconds, sir. And again, we are seeing this window, sir, at the radius of.
okay.
So no problem, sir. You can continue, sir. But if we come across
Yeah. If
again,
there is any difficulty, you tell me, right?
we will ask again, sir.
Okay. So repeat similar calculation at the radius of diffuser throat, right? So that is we calculate CW and assume CR and calculate C, then T, then P, then rho, then again CR and repeat it. And again you calculate alpha tan inverse CR by CW. Then the area is taken to be 5 dB into sine alpha. This becomes the area. And once you get this area by B into number of blades, I'll put some Z. So this gives me diffuser width, throat width. So when Z is number of diffuser gains. Okay, so this is the way we have to do the problem. And then I have to also 2 points. If there is IGV, consider pre-will. So this is one point I told. And another thing, if the compressor is,
Sir,
yes,
after pre-will, you got stuck, sir.
okay. So the pre-will modifies the inlet triangle like this. Okay, so I have to draw the modified inlet triangle. So whatever calculations I do, I have to do on this triangle. If IGV is not there, then it will be only right angle triangle. This is without IGV, and this is U, this is V, and this is CVA equal to 6. Here, this is CW, CW1. Okay, U1, V1, CW1, this is C. Okay, this is the way we have to introduce the IGV into the calculation or the pre-will into the calculation. And so if the compressor is in a aircraft that is moving. So the at some altitude, so you'll be given h and aircraft velocity. Okay, you should not. I'll put AC, aircraft velocity. So at h, I have to get the ambient conditions. Then you have to calculate uh, T naught 1 is equal to, or I can put EPA, TA. Okay. Then the ambient conditions,
Sir left meeting, right? Is it
Yes,
correct?
Guru.
Okay, okay.
Okay, can you see me now?
Yes, sir.
Okay, we'll go back. So where did you see
Sir,
this?
at the ambient conditions, sir. PA and TA.
Okay, okay, this what?
No, not before.
This
Yes,
one?
here, sir. T01 you are writing, sir.
Okay. So if it is flying, so the air comes with some speed into the diffuser first. So I have to find out what is the effect of diffuser, and I have to find out the inlet conditions for the compressor. So that is obtained. So ambient conditions are taken as static conditions, and I have to get the stagnation conditions which are at the compressor inlet. So TA plus aircraft square velocity square by 2 CP gives the stagnation temperature, and the stagnation pressure I will get from this. So once I get these stagnation conditions, then I have to do the calculations that I have done for the first problem. Okay, that is assuming CA and doing that. So those things I have to do. So this is the thing effect of inlet velocity. Okay, so that is the effect of inlet previously we have seen, and effect of aircraft velocity and compressor design calculations we have seen. So volute casing. So volute casing, there are three types of casings we have seen: rectangular, trapezoidal, and circular. And rectangular is preferred for blowers, and it is easy to manufacture and run maintenance. But circular one, it is used for compressors, right? Because but the manufacturing is a bit expensive because it is circular cross section. Rectangular cross section means just on both sides you just put sheets that will give you rectangular cross section. Okay, then coming to so with this we have completed centrifugal compressors. So we came to axial flow compressors. So in the axial flow compressors, first we have discussed about the relative merits and demerits. So if if it is static, if it is not moving, then the ambient conditions are taken stagnation conditions, as we have taken in the first problem, and we do it. Okay, then axial compressor relative to centrifugal compressor, the merits are it has high mass flow, that is merit, but it is low pressure ratio per stage, that is demerit. But though it is low pressure ratio, multi-staging is easy, and because of that, I can go for large overall pressure ratios. And it has high efficiency, but it has narrow mass flow range compared to centrifugal compressors. And it has high efficiency, okay, and low frontal area. Because of that, it is suitable for aircraft applications. But it is expensive because of airfoil cross section and all, and it is complex in designing, and manufacturing is expensive, and it has no self-cleaning character. That's why contaminated atmospheres we cannot use it, but in aircraft applications we use it. So these are the relative merits and demerits. And then we see what are the properties variations. So this we have discussed in the last class, the property variations across rotor and stator. So across rotor, W is negative, that is we are giving work. So absolute velocity increase, T naught increase, P naught increase. But when you come to stator, W is 0, Q is 0, so T naught is constant. And P naught constant if no losses, or P naught decrease if entropy increase. That is if losses are there. And coming to the both are diffusing passages. Diffusing passage means here relative to blade, relative velocity decrease. Here there is no relative velocity. In stator, absolute velocity decrease. Because velocity decrease, there will be increase in the pressure, increase in the density, increase in the temperature, increase in the enthalpy. Here also P increase, rho increase, T increase, and H increase. Okay, so this is the way the properties vary across rotor and stator. And then we have seen the cascade and the velocity triangles of axial flow compressor. Okay. So we have seen that the cascade should be a like this. So the velocity comes here like this. So the velocity comes here like this. So here there is more area and here less area. So area decrease or passes width decrease. So sorry, passes width increase. Passes width increase. So relative velocity decrease and pressure increase. So that's what we see. And so this is the relative velocity direction. And if you add this is U. And coming to this, so this is CW1, this is VW1, this is C2, this is V2, so this is CW2, this is VW2. And the angles we have taken absolute velocity alpha and relative velocity beta. So what is that you can observe is because W negative, C increase, so C2 greater than C1. So diffusing passes, so V decrease, so V2 less than V1. Okay, so that we have to observe. And another thing is U1 equal to U2 equal to U as it enters and leaves at the same radius. And so m dot is equal to rho A CA. And here rho increase and A decrease, because of which CA is equal to constant. So U is constant and CA is constant. That is the base and altitude of inlet and exit triangles are same. Okay, so these are the things you have to observe. And then we have derived various relations like U is equal to CW1 plus VW1 equal to CW2 plus VW2. So from which we get CW2 minus CW1 is equal to VW1 minus VW2. And also this is CA into tan alpha 1 plus tan beta 1 is equal to CA into tan alpha 2 plus tan beta 2. So these are the things we have seen. Or if I divide this by CA, U by CA, CA by U is flow coefficient. So I'll get 1 by 5 is equal to tan alpha 1 plus tan beta 1 is equal to tan alpha 2 plus tan beta 2. Okay, so this is one relation. And then we have got W is equal to U into CW2 minus CW1 or U into VW1 minus VW2, or this is equal to UCA into tan beta 1 minus tan beta 2. This is the second relation. So I can take this as the first relation. And so W by U square, if I divide by U square, psi is equal to phi tan beta 1 minus tan beta 2. Okay, so this is one relation. Like this. And then we have defined what is reaction. And the reaction is delta H rotor by delta H stator plus delta H rotor. So delta H of stage is equal to delta H naught of stage if C1 equal to C3. That is, if they are repeating stages. So repeating stage means C1 equal to C3 and alpha 1 equal to alpha 3. So, and delta H naught of stage is equal to W. So R is equal to, for delta H of rotor, it is H2 minus H1 by W. So H2 minus H1 is V1 square minus V2 square by 2 by W. Or CA square into secant square beta 1 minus secant square beta 2 by UCA into tan beta 1 minus tan beta 2. So if secant square is written as 1 plus tan square, so you are going to get CA square into tan square beta 1 minus tan square beta 2 by, again this is by 2 2UCA tan beta 1 minus tan beta 2. Okay, so one CA gets cancelled. So we are going to get 5 by 2 tan beta 1 plus tan beta 2. So this is the way we get. So this can be written in various ways. R is equal to 5 by 2 tan beta 1 plus tan beta 2 or CA by 2U tan beta 1 plus tan beta 2 or CA tan beta 1 is CW1 plus CW2 by 2U. And this also can be written as, because CW1 is U minus VW1, this I will write U minus VW2. So I am going to get 1 minus sorry, this is VW, I have written the other way. So here VW1 plus VW2 by 2U. CA tan beta 1 is VW1. Okay. And this can be written as 1 minus CW1 plus CW2 by 2U. Okay, so these are the various ways of writing the reaction. And so after doing this, if you are, we are checking what happens when R equal to 0. So on R equal to 0, because this is so this gives beta 1 equal to minus beta 2, means rotor blades are symmetric. So R equal to 0 means delta H across rotor is equal to 0. So delta P also, so P is V is equal to constant, P is equal to constant, and H is equal to constant across rotor. All pressure rise occurs across stator only. So rotor blades are symmetric or bucket type. Similarly, if R equal to 1, I am going to get alpha 1 equal to minus alpha 2. So stator blades are symmetric or bucket type because delta H stator is equal to 0. So across stator, P is equal to constant, H is equal to constant, and the velocity is constant. And all pressure rise across rotor only. Okay, so this is what we observe. And when R equal to 1, so this is what we have taken. So this is, sorry, 0.5. That is equal to half. So if this is equal to half, this and this goes off. So if U by CA is taken to the other side, so I will get 1 by 5 is equal to tan beta 1 plus tan beta 2. This is for 0.5 reaction. But we have already 1 by 5 is equal to tan alpha 1 plus tan beta 1. And also we have 1 by 5 is equal to tan alpha 2 plus tan beta 2. This is from inlet triangle. This is from exit triangle. So if we compare these two, so we will get that because beta 1 are same, but alpha 1 equal to beta 2. So we will get alpha 1 equal to beta 2. And if I compare these two, so we are going to get alpha 2 is equal to beta 1. So if you see the triangles, so we got like this, okay? So this is alpha 1, this is beta 1, this is C1, this is V1, and this is V2, this is C2, this is alpha 2, and this is beta 2. So we got alpha 1 equal to beta 2, alpha 2 equal to beta 1 means they become mirror reflections. Inlet and exit triangles are mirror reflections. And also we can say they are similar triangles. Not only that, so if alpha 1 equal to beta 2 and alpha 2 equal to beta 1, because they are mirror reflections, C1 equal to V2, C2 equal to V1. And this will become CW1, this is VW1, this is CW2, this is VW2. So we will get CW1 equal to VW2 and CW2 is equal to VW1. Is everything clear what I am writing?
Yes, sir.
Right. So all this we have discussed in the last class. I am just repeating. Okay. Here the thing is alpha 1, beta 1 and beta 2 are inlet and exit angles of rotor. And alpha 1, which is equal to alpha 3, alpha 1 is or alpha 3 is inlet angle of stator. and alpha 2 is exit angle of stator. So here this is exit angle of stator and this is exit angle of rotor. This is inlet angle of rotor, this is inlet angle of stator. So means both inlet angles and exit angles are same for stator and rotor. Beta 1 inlet angle of rotor, beta 2 exit angle of rotor. But alpha 1 is exit angle of stator because alpha 1 is alpha 3 at which it is entering the stator, and alpha 2 inlet angle of stator. So because we have alpha 1 equal to beta 2, inlet angles are same for stator and rotor, and alpha 2 equal to beta 1. Okay, this is these are exit angles. Inlet angles are same for stator and rotor. So what it means is, because both inlet angles and exit angles are same, we can have same blades on stator and rotor. Why? Why? Because delta H across stator is equal to delta H across rotor. So because of that, same blades can be used on stator and rotor. So this is the advantage of 50% reaction blading. So if I have repeating stage and if I design it for 50% reaction, I can have same blades for all stators and all rotors of all the stages. Am I clear about this?
Yes, sir.
Yeah. So this is interesting thing. And here one more interesting concept I will tell. So if I take the velocity triangles, base of both triangles, bases of both triangles are equal, and heights of both triangles are equal. Because bases are equal, both triangles can be drawn on same base. Both triangles can be drawn on the same base. So that's what we do with the same height. So what I do is inlet triangle large V1 small c1 and exit triangle small v2 large c2. Okay, this is v1, this is c1 inlet triangle, and u is same for both. Height is same for both. And for inlet triangle, this is alpha 1, this is beta 1, and this is c2, this is v2, this is alpha 2. Okay, so this is the way I can overlap both the triangles. Okay, here I will tell you some interesting things, right? Suppose, because normally I am interested in non-dimensional things, right? Okay, and here I will put these things also. This is CW1. This is VW1. This is VW2. And if I make them non-dimensional,
Sir,
yes,
sir, why relative velocity at exit is decreasing compared to inlet?
that's
Any
what I'm
reason?
telling. This is diffusing passes. So relative
Okay,
to
okay, sir.
blade, because the width is increasing, that's what I told. Okay. So rotor, the cascade, if you take A increase, and because of that relative velocity decrease and pressure increase, density increase, temperature increase. That's what I am telling, right?
Yes, sir.
Okay. And now I try to make the triangles non-dimensional. Divide all the velocities by u. Okay. So this is CA by u, C1 by u, C2 by u. Like this. So I will get like this. Will the triangles be different? Angles, will angles change or same? Will it be same?
Same, sir.
Same, because just I'm scaling them, right? So angles will not change. Angles will be same. Okay. So everything gets zoomed out or zoomed in. Okay. So this is the way we get the triangles. So what is the base of the triangle?
1,
Yeah, is equal to 1 unity. And height of the triangles?
5.
Height of the triangles is 5. Very good. So that is flow coefficient. Okay. Now, if you see here, what is the distance between these two? I can write this as, see, this is CW1 minus CW2. Or I can write that as VW1 minus VW2. CW2 minus CW1 by U, or VW1 minus VW2 by U, like this. Am I right?
Yes,
Yes,
sir.
sir.
So what is this actually? If you remember, psi is equal to UC, okay, W is equal to
VW1 minus VW2.
W is equal to UCA into tan beta 1 minus tan beta 2, or U into CW2 minus CW1. Okay. So W by U square, which is psi, is equal to CW2 minus CW1 by U. Okay. So this is psi. So means the distance between the two vertices will be equal to psi. Am I clear?
Yes,
Yes,
sir.
sir.
Yeah. And so here one more thing I will do. From this point, this is VW1 and this is VW2. So VW1 plus VW2, it will be, if I take the center point here and if I draw, so this will be VW1 plus VW2 by U. Okay. And so what is VW1 by VW2 by 2U? Average of VW1 by U and VW2 by U. If this is VW1, this is VW2, right? So this distance will be equal to Vw1 by plus Vw2 by 2u, which is reaction. Is that clear? If you want still to be clear, so this is Vw2 by u, and what is this distance? This is half of this,
5 by 2.
plus Vw1 minus Vw2 by 2u. So if I take 2u here, so what is that I'm going to get? Vw1 plus Vw2 by 2u. Okay, and what is Vw1 plus Vw2 by 2u? Here we have written that reaction. Yeah, Vw1 plus Vw2 by 2u is reaction. So this is reaction. So if I take the center point of these two vertices and draw vertical, so the distance from the left corner to this is reaction. And if
This is
I,
all for a reaction 0.5 only, guys.
yeah, 0.5.
Yes, okay.
It need not be 0.5.
Sir, for that only VW1 plus VW2 by 2 is equal to
No,
R2.
no, 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 no. That is reaction general formula. Just I will show you. So this is general formula, 5 by 2 into tan beta 1 plus tan beta 2, VW1 plus VW2 by 2u, 1 minus CW1 plus CW2 by 2u. All these are general formula for reaction. It is not for 50%. If 50%, then this is equal to half, and VW1 plus VW2 will become u. Because so VW2 is CW1, so CW1 plus VW1 is equal to u, we know it. So this is the way it happens for 50% reaction. But this is general formula for all triangles. Am I clear?
Yes.
Like this. Okay, so this is reaction, and to this point, if I draw a line like this, okay, so this velocity is called as Vm by u. Vm. V1 is this, V2 is this. I am taking some point in between, and this I call it as Vm. It is not exactly mean velocity. It is not average of V1 and V2. Vm is not V1 plus V2 by 2. This is not V1 plus V2, but VWM, will component of Vm, is equal to VW1 plus VW2 by 2. Okay, and VWM is Ca tan beta m, if this is beta m. This is equal to half into tan beta 1 or Ca by 2 tan beta 1 plus tan beta 2. So this is important. Tan beta m is equal to tan beta 1 plus tan beta 2 by 2. Or VW1 plus VW2 by 2 is this. So here, if I take reaction is Ca tan beta m, or Ca by 2 into tan beta 1 plus tan beta 2, or VW2 1 plus VW2 by 2, like this. Okay, this particular relation we use it later.
Sir, why C2 is more compared to C1?
Yeah. Why? Because I am giving work to this. Okay, I am
What
giving work
relative
means
velocity decreasing?
I am giving work means H naught increases,
Yes, sir.
right? So where is that going? It increases the kinetic energy.
Then sir, relative velocity decreasing. Na?
Relative to blade, the velocity decrease, but absolute velocity of the fluid. Okay, because I am giving work to the fluid,
Okay, sir.
so there will be increase in the absolute velocity because of the work given to the fluid. But relative velocity decreases because the passage width is increasing.
Yes, sir.
Okay, relative to blade, it increases, but absolute velocity of the fluid increases. So because of the absolute velocity fluid increasing, I am having large kinetic energy when it is coming out of the rotor, right? So that I want to convert to pressure energy by having stator, because stator is again a diffuser where absolute velocity decreases.
Okay,
So
sir.
in rotor, relative velocity decreases. In stator, absolute velocity decreases. In both, pressure increase. Okay?
Yes, sir.
Yeah.
Yes.
And so these particular non-dimensional velocity triangles are important. Okay, here, actually this concept I heard from my professor in IISc Bangalore. I really liked it and enjoyed it. I never have seen anywhere. Okay, so here, if I draw the non-dimensional velocity triangles, the base is unity, the height is flow coefficient, that is, it represents the flow. If more height is there, I have more flow. If less height for the triangles is there, it is less flow. In the same way, the distance between the vertices of both the triangles, that represents pressure ratio or work. If they are away from each other, there will be more work or pressure ratio. If they are together, there will be less pressure ratio. Am I clear?
Yes, sir.
So if I assume the velocity triangles are elastic, and if I take the both vertices, and if I take away from each other, its pressure ratio increase. If I am bringing together, pressure ratio decreases for the same height, for the same flow, for the same blade velocity. Okay, just pull it away from each other, pressure ratio increase. Pull it near to each other, right? Then the pressure ratio decrease. Am I clear? Okay.
Yes.
Yes, sir.
And one more thing is, now I keep the height same. I keep the distance between the vertices also same. And I keep the two vertices, I catch it, and together I move towards right. Phi is same, psi is same. What happens to reaction? This center point moves to the right. So this center point moves away from this vertex. So there will be increase in the reaction. Am I clear or not? The distance between the vertices I keep same. The height of the triangle is same. And I catch these two vertices. I just move it towards right. That center point moves towards right. Am I clear?
Yes, sir.
Then what happens to reaction?
Increases.
Increase in the reaction. But if I bring it to the left side, the reaction
Decreases.
decreases, right? And if I move it to the left side in such a way that this particular line comes to this point, then what happens to reaction?
Zero.
Zero.
Zero. So if I change that position in such a way that this center line goes through this, the reaction is zero. And if I move to the right side in such a way that the center line comes to this point, then what happens to reaction?
1.
1. Okay, so that is the way we can, if you are asked to draw the velocity triangles for 0 reaction and reaction 1 and 50% reaction, how it look like. So if this is going through the intersecting point like this is 50% reaction. Am I clear? If the center
Yes.
line goes to the intersection of these diagonals, then this is 50%. Exactly, both triangles will be same. So if I just, I will show you how to draw it. Actually, I will, in the class, if it is offline, I will ask you people to draw it. Okay, the 0% reaction and 100% reaction and 50% reaction, I normally ask. Okay, so suppose if I take the velocity triangles, okay, base I will draw here. Okay, if I draw the base here, and so the center point, center line should go like this. So the both vertices will be like this. So I have brought these two vertices to the left side in such a way that the center point goes through this. Okay, now I draw the inlet triangle. So inlet triangle will be like this. And the exit triangle will be like this. So inlet triangle, exit triangle. It will be like this. Am I clear? And so for the inlet triangle, this is alpha 1, this is beta 1. And for exit triangle, this is alpha 2 and this is beta 2. R equal to 0. Okay, what are the observations we can make here? Is V1 equal to V2. Am I clear? And beta 1 equal to beta 2 or minus beta 2, I can say. So this is what we have observed for 0% reaction. So because V1 equal to V2, symmetric rotor blades or bucket type. If I draw R equal to 1, so again draw the base and the center line should go through this other extreme. And again, if I draw the two vertices of the triangles, okay, so this will become the inlet triangle. So this is V1, this is C1, sorry, C1, and this is alpha 1, and this is beta 1. And for the exit triangle, it comes like this. This is V2, and this is C2. And so this is alpha 2, and this is beta 2, like this. So for 100% reaction, what is that we observe? C1 equal to C2 and alpha 1 equal to minus alpha 2. So because C1 equal to C2, the entry velocity and exit velocity for stator is same. Okay, so stator blades are alpha 1 and alpha 2 are angles of stator, or symmetric, or bucket type. Is this clear? So this is the way I can draw. It is just for drawing how the velocity triangles will be. But normally for axial compressors, we never use either complete impulse type or completely reaction type. The reaction varies around 0.5. Okay. So if R is equal to 0.5, So then what will happen? Through the center point, this center point will come and the vertices will be exactly on these two sides. So this will be the one triangle, exit triangle, and this will be the inlet triangle. So this is V1, this is C1, this is V2, this is C2, this is alpha 1, this is beta 1, and this is beta 2, and this is alpha 2. So alpha 1 equal to beta 2, alpha 2 equal to beta 1, C1 equal to V2, C2 equal to V1, CW1 equal to VW2, VW1 is equal to CW2. So like this, and similar triangles, mirror reflections, so same grading. So all these things will come for the 50% reaction. Okay, so base is unity, and this is phi, and this is psi, and R equal to 0.5 here. In the previous one, R equal to 0 here. This is U, and also equal to R is equal to 1. This is phi, this is psi, this is phi. So what I want to say is, by seeing, if you are you want to purchase some blower or a compressor, so you see the velocity triangles. Okay, so velocity triangles may look different. You don't know how to compare. Then just non-dimensionalize them. So once you non-dimensionalize, then you understand these are the velocity triangles for one compressor and these are for another compressor. So by seeing the heights, you can see which gives me large flow. By seeing the two vertices, the distance between the two vertices, you can see which gives me high pressure ratio. And by seeing the distance between the left vertex of the triangle, left extreme of the triangle, and the center point of the two vertices, so the distance gives you reaction. So what is the reaction also you can understand by seeing the velocity triangles, and you can compare two velocity triangles. Am I clear about this?
Yes, sir.
Right, this is very, very important. It gives you a complete concept of it. Usually you will not get anywhere, right? Any book you will not get this. This is from my sir, and I am telling to you, right? So any questions till now? Okay, then I will stop here. Okay, this one more thing. Next week, this is mid-semester week. So we will have mid-exam in that week. So I planned for Wednesday 10 to 12. And if you want to change one day this way or that way, or if you want to change the timing from morning till evening, so whatever, you tell me. But it will be just within 1 or 2 days. Which day and which time you want? Bharat, will you want to discuss and tell it, or shall I fix it?
Sir, I'm going to discuss with the people, sir,
Yeah,
because we already have 24th
yeah,
and
yeah.
25th.
Because
Sir.
other people also may conduct it,
Yes, sir.
right? So you decide about that. But it should not be much deviation from my date and time. Okay.
Okay, sir.
So try to make it Tuesday, Wednesday, Thursday, one of the days in between. So because now it is Friday, I thought Saturday, Sunday, Monday, Tuesday time will be there for study, and Wednesday will be better.
Yes, sir. Okay, sir.
Okay. Right. So we will have a small story then, if no questions are there. Any questions?
No, sir.
Okay. So it's a nice story. It's a teacup story. There was a couple who used to go to England to shop in beautiful stores. They both liked antiques and pottery and especially teacups. So they collect teacups, right? Different shapes, different sizes, different designs, and all. They collect teacups. So they have gone in an antique shop. And one day, on their 25th wedding anniversary, in a beautiful shop, they saw a beautiful teacup. And they said, "May we see that? We have never seen one quite so beautiful." So, as the lady handed it to them, suddenly the teacup started speaking. "You don't understand," it said. "I haven't always been like this. There was a time when I was red and I was clay. My master took me and rolled me and patted me over and over, and I yelled out, 'Let me alone!' But he only smiled, not yet. Then I was placed on a spinning wheel," the teacup said, "and suddenly I was spun around and around and around. 'Stop it, I am getting dizzy,' I screamed. But the master only nodded and said, 'Not yet.' Then he put me in the oven. I never felt such heat. I wondered why he wanted to burn me, and I yelled and knocked at the door. I could see him through the opening, and I could read his lips as he shook his head, 'Not yet.' And finally the door opened. He put me on the shelf, and I began to cool. 'There, that's better,' I said. And he brushed me and painted me all over. The fumes were horrible. I thought I would gag. 'Stop it,' I cried. He only nodded, 'Not yet.' Then suddenly he put me back into the oven, not like the first one. This was twice as hot, and I knew I would suffocate. I begged, I pleaded, I screamed, I cried. All the time I could see him through the opening, nodding his head, saying, 'Not yet.' Then I knew there wasn't any hope. I would never make it. I was ready to give up. But the door opened, and he took me out and placed me on the shelf. 1 hour later, he handed me a mirror, and I couldn't believe it was me. "It's beautiful. I am so beautiful." "I want you to remember then," he said. "I know it hurts to be rolled and patted, but if I had left you alone, you would have dried up. I know it made you dizzy to spin around on the wheel, but if I had stopped, you would have crumbled. I knew it hurt when it was hot and disagreeable in the oven, but if I hadn't put you there you would have cracked. I know the fumes were bad when I brushed and painted you all over, but if I hadn't done that, you never would have hardened. You would not have had any color in your life. And if I hadn't put you back in that second oven, you wouldn't survive for very long because the hardness would not have held. Now you are a finished product. You are what I had in my mind when I first began with you." This simply is a wonderful demonstration of how God works in all of us. He changes us little by little from glory to glory. On the way to glory, though He will have run ins with sufferings and trials, and it likely will be painful. I'm sure there will be time when we, like the teacup in progress, we call out to God asking Him to get us out of the situation or circumstance or just take it all away somehow. And all God will say is, "Not yet." The encouraging thing is He knows who you are and what you are capable of, and He desires to refine you and make you into His perfect image. Although we just see the clay in ourselves, those flaws and imperfections, He sees the teacup, the beautiful finished product. He is still working on you, always. And if you will allow Him to do His work, you will notice that He can do some pretty amazing things with your life, far more than you can even dream of. Okay, so that's the story. Thank you very much. All these adversities, all these sufferings, all these pains in our life are to make us more beautiful and strong and attractive. Right? Thank you very much. See you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.